broadcast is now starting. All attendees are in listen-only mode.
Good day, this is Fiona from the FEKO marketing team, and I'd like to welcome everyone to this webinar today. Andries Maritz will be presenting on the topic Lua scripting and general automation in FEKO. A recording of the presentation will be available within 24 hours. A notification email will be sent to you providing a link to the presentation. We encourage you to post questions for Andries throughout the presentation in the area provided on the right-hand side of your screen. You do not have to wait until the end of the presentation to post your question, but Andries will probably only answer them at the end of the session if time allows. For further information on FEKO, please visit our website or contact your local distributor. You are also welcome to contact us via the email address that appears at the end of the presentation, webinars@emss.co.za. I will now hand over to Andries. We hope that you enjoy our presentation.
Hello everybody, and thank you Fiona for the introduction. This is going to be a brief overview and introduction to how Lua scripting can be used in the FEKO suite to improve the workflows and hopefully make your lives a little bit easier. So, as with everything else, we start with the basics. So the first question is, what is Lua? Lua is a scripting language. It is a very small, very fast, very powerful embeddable scripting language. It's a very easy language to integrate into larger application suites such as FEKO. It's used by a variety of industries, most prominently in the gaming industries, but also by applications such as Adobe Photoshop Lightroom or the Firefox web browser or VLC media player. And how we use it is to provide a means for our customers to extend the functionality that comes as a default to the FEKO suite. FEKO provides two different types of scripts. The first kind is the API script, which is the application programming interface scripts. These provide the users with the means to control the application, so it can simulate button presses or creation of certain configurations and dialogues and so on. They are stored externally to the post-FEKO session or CAD FEKO model as a .lua file, and this makes it possible for them to be reused easily. So there's also an application macro library that has been built into both of these applications. And once you've written a script, you can place it on a central repository and easily relaunch them at a later time. Now, the API scripts are also special in the sense that you can create custom dialogues. In other words, you can create your own GUIs. And this makes it possible to interact with the application and with external applications in a level that hasn't been possible in the past. The second kind of script are math scripts, and these are essentially used within a post-FEKO session to process simulated result data. They live inside a post-FEKO session file or a PFS file, and these are usually the kinds of scripts that you write if you want to quickly alter and modify results in a specific way that isn't supported by default in the application. We typically use API scripts more often than the math scripts, but both are useful depending on the situation. The scripts can be generated in the Lua editor. These are available both from CAD FEKO and post FEKO. And they provide you with the ability to work with multiple scripts at the same time. Then there is a script editing area and an interactive console output area. We will, at a little bit of a later stage, go through an interactive example and maybe look at these concepts in a little bit more detail. An external Lua script can be written in any text editor. It's just a simple text file, but our built-in editor does provide little benefits such as syntax highlighting and auto-completion that makes it easier to create a script in the FEKO context. Our first example that we're going to look at is a simple automation example. Now, as stated earlier, the automation examples are commonly used to drive the applications themselves. In other words, aspects of the application or a session can be modified. So our example for today we're going to be looking at a post-FEKO session. The post-FEKO session contains multiple views and multiple graphs, and the utility will open up a dialog that asks for the user input or for the new window names. So this window renamer utility would make it easier for you to see what graphs contain what data. So let's take a quick look at that post-FEKO session. Here we have a post-FEKO session of a horn model. It's got the 3D view with the near field in the aperture. And on each of the three graphs, I've basically plotted a line across the x dimension and a line across the y dimension. The first graph plots the electric field component. The second graph contains the magnetic field component. And the final graph contains the power or the pointing vector. But when you are looking at the session as a whole, it's difficult and quickly becomes hard to see exactly which graph contains which results, and especially if you have multiple models, this can become a tedious process. So I've written a little script and added it to the application macro library. There's the window renamer script. When you launch it, it assesses the post-FEKO session and provides you with the user dialog where you can now say what the new view name should be. And you will note that when you run the script, the window names are now changed as specified on the dialog. Okay, that's just a small example, but hopefully it gives you some idea of what automation scripts are capable of. And when we move on to the next example, the next small example illustrates how a math script can be used to process simulated data. So what our example is going to be doing is looking at the simulated near field and looking at the energy density inside certain dielectrics. Now the model setup is a dipole surrounded by 4 cubes, and each of the cubes have different dielectric properties. They're just arbitrarily defined as the epsilon r and mu r, the permeability and permittivity to 4, 9, 16, and 25 respectively. And we use these properties to calculate the energy density as indicated by the equation down at the bottom of the slide. The electric energy density is simulated as a function of the permittivity and the electric field magnitude. And the magnetic energy density similarly with the permeability and the magnetic field magnitude. So let's take a look at that script or that session. Here we have the model. As you can see, it's a dipole that's surrounded by the 4 cuboids. And in our project browser, we have a custom math script. And this math script contains the same, let me just plot the near field. It plots the same spatial axes as the near field with the custom quantity of electric energy and magnetic energy densities. So as you can see now, our new custom result, you can plot whichever one of the two components are required. And we will look at an interactive example in a moment, but just quickly show you what the script looks like. What we do is we obtain a copy of the near field data and a copy of the near field's media information, in other words, the dielectric properties in which each near field point was simulated. And then we run through and we calculate the electric and magnetic energy densities as indicated on the slide previously. So this hopefully illustrates that you can, for simulated data, process the data into a very customized format without having to export the data into an external format for processing in a different application. It can all be done inside post-FEKO. Okay. Now, the scripting, the script that I just showed you might have seemed a little bit daunting. The Lua language itself is actually quite simple, but the API to the FEKO suite is complex due to the complexity of the applications themselves. So we recommend that you start by, first of all, going through the Lua language basics. These are available online. You will see on the internet there are links to the various tutorial and reference manual sites. And then we also have a full API documentation in our online help and PDF manuals. And these, let me quickly show you, can be obtained by standing in the script editor and pushing the help button or pushing F1. And it will give you more background information, also with all of the links and useful information there. Now, if you look at the post-FEKO API documentation, this is a set of documentation that is generated for each object that can be modified in the application using automation and math scripts. And if you look at the application itself, you can see that many of them have small examples that hopefully illustrate just how to get a handle and how to set some of the basic properties. The application, for example, post-FEKO, contains a collection of graphs and models and views and store data and so on and so forth. And you can perform certain actions on them, such as clearing the session and creating a new project and so on and so forth. This does take some time to get used to, but hopefully the examples will give you a very good starting point, as well as the other examples that have been made available. And on that note, we also provide a script repository on the FEKO website. It's the one that's highlighted in red. Hopefully you can find an example or two that shows similar concepts to what you're trying to achieve. Okay, let's take a quick look at a simple example. This is just to demonstrate how the editor works and hopefully give you a taste of what programming in Lua entails. What we're going to be doing is I've simulated a near field around a car chassis. That's the blue area that you see there, with a source on the top of the roof, typically where an antenna would be placed. And we've simulated it for the 90 megahertz and 2400 megahertz bands. Now these roughly correspond to, say, an FM radio or a Bluetooth or Wi-Fi signal. And what we're going to be calculating is the summation of the electric field components. So in essence, we're interested in the superposition between the two field magnitudes. And what we will be seeing is the electric field for the first component, plus the electric field component for the second near field, and then obtain the one that's on the right. Okay, so let's take a look at that and see if we can get an example running. So here's a post-FEKO session that contains the 90 megahertz model and the 2400 megahertz model. And we're going to be creating a custom math script that contains just the magnitude of the electric field component. So to do this, we click on New Script, Add Math. Now we're not using one of the built-in result types. We're creating a custom quantity, in other words, the magnitude of the field component. So we'll be using a custom math script for this purpose. Okay, now the first thing that we need to do is get a handle on our two near field objects. So we need to name them and get the data into the scripting environment. So just to do this, I'm going to go to the interactive console and I'm going to print a list of all of the near fields in this session. Now the first one is the 2400 megahertz model and the second one is the 90 megahertz model. So let's now say near field 1 equals PF. And as you can see, there's an autocomplete box that pops open. And as you go on, it tries to complete with the most sensible autocomplete options for our purposes. So we want to get the data set for the first model. Let's take the 90 megahertz one first, and then do the same for the other one. So now near field 1 and near field 2 should be stored in each of these different result handles. Now you'll notice if you run a math script, you will get an error. Oh, save the session quickly. That says that the script must return a data set. That's because the math scripts require a data structure that contains values, and we haven't returned one yet. Now the data set that we're going to be returning is going to be a new custom data set. So what we're going to do is say new data set equals a new data set object. And this is now a blank data set. It doesn't contain any axes or quantities. Now an axis and a quantity defines a data set as follows. Let me show by illustrating how the near field looks. The near field that we're looking at contains a frequency axis. Each of these two have a single value at their respective simulated frequencies. They contain an x-axis, a y-axis, and a z-axis. The x and y range over a set of values, whereas the z is at a single value. And each of the near fields contain the x, y, and z electric field components and the x, y, and z magnetic field components, as well as an index into which medium or dielectric medium the near field point resides. Now all of these would be free space for our case at the moment. What we are interested in is to copy these three axes into our new data set and to process the electric field components for both near fields into a magnitude. So let's start by copying the axes across. We are going to be skipping the first frequency, so we're going to be running from the second axis over to the final axis count. So now we're going to be iterating and copying these three axes. So we want to say new data set axes. We want to add the near field axis at that position, and you can see that we've now copied the three axes across, but we haven't added any quantities yet, which is also given by our error message down there. So now we want to create a new quantity. This is done in a very similar way, except instead of an axis, we now want to add a quantity. Now, since this is a custom quantity, we can basically specify anything that we would like. So let's say the E field and since this is just going to be the magnitude, we will be looking at a scalar value. So this is going to be a data set quantity type scalar, and the units will be volts per meters, since this is an electric field component. Now if we run this again, no errors, and if we look at the data set again, you'll see that we now have a data set that contains three axes that have the same properties as our near field, and we've got a single quantity that stores the combined E field. Now this data set doesn't contain any values yet. All of the values are undefined and uninitialized, so now we need to iterate over the near fields and add them. So to do this, we're going to create a simple nested for loop structure. So looking at the x values, it's got a count property that gives the number of elements in that dimension, and we're going to be doing the same for y and z. Now don't worry about trying to keep up with the code. This webinar will be made live or available as a recording later, so you can look at it in a little bit slower pace later. But for now, let's just demonstrate the concepts. Now, we need to iterate over the 3 axes that the new dataset contains, but we also need to index into the original near fields. So what we're going to do is we're going to store an index into each of the near field simulations at this specific point. So in the innermost loop, you basically say the first near field, we want to look at the first frequency at the X position that we are at now, the Y position, and the Z position that we are at. And then similarly for the second component. So each of these 2 values now point to a specific point in the near field. The first one for the 90 megahertz near field and the second one for the 2.4 gigahertz near field. So to obtain the magnitudes, we can say the near field electric component 1 magnitude and we're taking the RMS value of this. So this is just the square root of the sum of the squares. So that's the magnitude of the electric field component for the 90 megahertz model. Now similarly, we want to do this for the second near field as well. So we just replace the 1s with 2s. Make sure that we replace the right ones. Skip that one. There we go. So now we have the magnitude of the 2. And now finally what we wanted to do from the beginning was to say the new data set at this X position, at this Y position, and this Z position has an E-field combined value that is basically the sum of the 2 magnitudes. Now, if everything is done correctly, we should be able to run. Don't get any errors, and we should now be able to plot this custom math result. And as you can see, this is now a larger value than the original one. Just goes from there to there. Okay. So this was just a quick script. Now this lives in the post-FEKO session. And as you can see, it's not a very long script, but it does take a few minutes to write. So automation scripting is also useful if it's something you're going to be using repetitively. But for those, let's quickly see what the effect of something is type of investigations. The math scripts are very handy. Okay. So that was a quick demonstration of the script editor as well as how we can actually set up a math script. Okay, now I can sit back and relax. The final example that I'm going to show you is a little bit more advanced. It also spans across CAD-FEKO and post-FEKO, so it deals with file manipulation and with writing of files and generation of models and then processing of results in post-FEKO. So actually what I've done is write 2 scripts, one for CAD-FEKO and one for post-FEKO, and we will be looking at doing a parameter sweep study for a model. So the model is a slotted waveguide antenna, and we're interested to see what the effect is of the slots offset from the center line and what the length of the slot is on the simulation results. So in order to do this, we have to start with a base model that contains parameters or variables for each of these 2 properties that we would like to vary. And then to launch the script in CAD-FEKO that generates models for each permutation and runs the kernel. And finally in PostFEKO we've got another script that combines all of the results of this data into a single result. So let's look at the CAD-FEKO model quickly. Here's our CAD-FEKO model. The slot length and offset have been defined as variables. As you can see, the slot length is defined parametrically as a function of the free space wavelength, and the slot offset was just defined as 0. So I've added the scripts to our application macro library. If you launch the script, it runs through the model's variable list, and it basically isolates all of the model parameters that we can set. And we're interested in looking at these two values, the slot length and slot offset. Now you can specify the start and end values. Let's look at it from here to there and choose 4 steps in between. And the slot offset we're going to look at from 0 to 6 millimeters. Note that my model was defined in meters, so everything is defined parametrically in that sense. Okay, now we also have to decide where we would like to store all of these model files. So it automatically suggests a parameter sweep directory for us, but you can also choose your own directory. As you can see, I've already simulated some of these results, so I'm just going to show you the generation phase in this model, and I can turn off running the FEKO solver by checking that checkbox. Now, when I click next, what's going to happen is the CAD-FEKO script is going to modify the model and save each permutation to that subdirectory. So let's see what that looks like. I've made a mistake with sorry about that. Okay, let's try again. Okay, so we choose 4 steps in each of those 2 dimensions. There we go. So now you can see that the models are modified and saved as different permutations. Now what the script also does is it creates in the directory that we specified an XML file, and this file basically just contains the path. So it says that this model corresponds to a slot length of 0.012 and a slot offset of 0, and it does so for each permutation of our sweep. So this file is going to be the bridge between CAD-FEKO and PostFEKO. So let's go to PostFEKO. Now you don't need anything open for this to run, so let's just make a clean session. If you run the script in PostFEKO, you're given a dialog that asks where the XML file is stored. Now I'm going to look at our pre-simulated results because they actually have data that we can process, but the models are identical, and process this XML file. And what the script then does is it parses the file and it loads each of the permutation models, and then it creates custom data from all of the simulation results that contains the 2 axes that we've swept across. So it's busy processing now, and you'll see in the tree on the left-hand side it starts to populate the data. Let's just close all of these views quickly. Okay, so you can see that it found a power block and 2 far field blocks. So if you look at the original model, this is just one of the permutations. We have far field pattern simulated in the co and the cross polarization axes, and each of these models contain a different slot value, slot offset and slot length. So when we look at the far field patterns, you can see for our newly simulated or newly processed data, we now have two options, one for the slot offset and one for the slot length, and the data differs as we set it. Now, this should correspond to the final one. This just makes it easier to deal with the data. So there you go. That's a parameter suite utility that should hopefully make it easier to investigate the effect of a variable on your model results. So what this automation example demonstrates is, again, how we can create custom dialogues, but also how we can analyze a FEKO model and modify the model, as well as how we can write our own custom files and then process those same files in post-FEKO or in FEKO as well if you would like, and how we can generate data that contains new, unique, and interesting results. Just out of interest, this took approximately 2 days to write the script, so it's another mechanism to quickly and easily extend the functionality that already exists in the FEKO suite with custom workflows. This makes it hopefully easier for you to share these workflows with other colleagues as well. So we've taken a quick look at what Lua is and why we've decided to use it, and then we've taken a look at the difference between automation scripts and math scripts. We've looked at how we can go about finding help on how to start using Lua and also what examples are available. And we've done a demonstration of how the script editor can be used to write small scripts, and then also given a demonstration on some of the more advanced usefulness of the automation environment. I hope that was interesting. If you have any questions or comments or feedback, you're welcome to email at webinar@emss.co.za. Thank you very much for your attention, and hope you have a nice day.